Okay, it's my great pleasure to introduce Rico Sennrich. He is a professor at the University of Zurich and a lecturer at the University of Edinburgh. I know his work through the byte pair encoding paper that he wrote. And that paper is attracting a lot of attention these days and is taking off because it's really fundamental. Whether you're using the modern type language models like BERT and GPT type language models, people are using that work. Rico's recent research has received funding from the Swiss National Science Foundation, ERC, and the Royal Society and Industrial Collaborations. And he has focused on machine learning for natural language processing, specifically high quality machine translation, transfer learning, and multilingual models. And today he's gonna be telling us the lessons that he learned from multilingual machine translation. So the virtual podium is yours, Rico.
Thank you for this introduction and thanks for the invitation. Good afternoon, everybody, or maybe shall I say good night, because it's a bit after midnight here, dreary night, rainy. I wish I was in Colorado with you and could give the talk live, but here we are. Let's try to do the best. So I called this talk Lessons from Multilingual Machine Translation, and I want to talk a bit about multilingual machine translation in the second part of the talk. And we'll see what lessons we have learned in our recent research. But I wanted to also talk a bit about machine translation in general, because I hear it's quite a diverse audience here. And maybe it's good to also set the stage, if you will, for what I'll be talking about next. So just to talk a bit about the past and future of machine translation, I have two symbolic pictures here. I'm not claiming that the ancient Egyptians already did machine translation, but the Rosetta Stone here is actually a bit of a mascot of machine translation, has become a bit of a mascot of machine translation, because it helped us decipher the hieroglyphs, because this is a stone that has the same text written in the hieroglyphs and the Egyptian demotic script and ancient Greek. And based on having this parallel data where you have the same text in different scripts, people were able to decipher this alphabet, which was before undecipherable. And this is really the foundation as well of modern data-driven machine translation, where we take data that has already been translated, even though the machines don't know anything about language beforehand. This data is enough for them to learn translation. Of course, we'll use a lot more than just a few lines of text for that. And a picture representing the future. I think this might be 40, 50 years old by now, this image where like this science fiction idea of universal translators in Star Trek. And nowadays we have actually reached this in a limited way, that we actually have now phones that we can use for instant translation, which was science fiction a couple of decades ago. But we still have a lot of way to go, and we'll talk a bit about where the current limitations are. Just like a one slide mathematical introduction to what we do in machine translation for those who are not familiar with it. So we're basically trying to solve the problem where you have a source sentence, which is just a string of symbols, words, characters, or whatever, and we want to try to find a translation for some source sentence. And what we're going to do is we are going to assume that we can learn probabilities of translation from the data that we have. And what we'll then need to do is find the most probable translation given the source language, which we're just going to make the assumption that a translation which will be probable under the model will also be a good one. Now, of course, we haven't seen a sentence that we want to translate before, so we have to decompose this just into a sequence of units. We can just use the chain rule here. So the translation probability will then just be the product of each word, given all the previous words or symbols in the target sequence and all the words or symbols in the source sequence. Um, so this is the mathematical model. To train this, we need lots of human translations. We're talking about, you can start very poor models, maybe with tens of thousands of sentence pairs, but like the modern commercial systems in high resource languages will be trained on tens of millions of translations. The lucky situation, this is probably a lot better in machine translation than in for a lot of other natural language processing tasks, is um, that this data is being produced anyway, because people rely on translations every day. There's a huge human translation industry, whereas for other tasks you might have to actually pay people especially to just create your training data. And then just one line about evaluation, because this will crop up every now and then, this so-called blue score. So if you want to know how good a translation is, this is actually a challenging thing because there's many good ways to translate the sentence. But we're just going to make an approximation. We're going to take a human evaluation, a human translation of that sentence, and we're going to measure the similarity to this human reference translation, and this measure is called blue. So higher will be better. Okay, so it sounds easy at first. Just get the probability of each word given all the previous words and all the words in the source sentence. But we actually quickly noticed that this is really hard to estimate, because most of the inputs for this probability distributions we have never seen before. So what people try to do in the good old days, and I'm talking like until like 5 years ago, was still using that probabilistic framework, but before the neural approaches took over, people tried to solve this by decomposing the problem into smaller units, like phrases which are just word sequences or some syntactic units, and then make some independence assumptions between them. Um, and this didn't really work well. It often produced word salads. Some of you might have had experience with that, using these systems a decade ago or more. And people try to bring in like more context, maybe just on the target side with a language model, but you end up having like a combination of multiple models, which are problems of their own were quite weak, and the generalization to new inputs was quite poor. What happened with neural machine translation in the last 5 years, and you will see in a bit that this has really revolutionized the field, is that this combination of weak models with independence assumptions was abandoned. And instead, we now have a complex neural architecture which models this probability of the next word given the context. Um, and what you really need to have, and there's different architectures that can achieve this, what you need to have is to get vector representation of all your input, to then make the probability estimate. And the nice thing about these neural architectures is that you can train this end to end. And what is also crucial about this to work is you can generalize to contexts that you haven't seen before, by exploiting the continuous representation in the vector space. You can just see an illustration of this on the right side here. So the general idea is that you here what you see is that like different geographical names are close together in this vector space, and person names are close together, verbs are close together. This is not something that you give the model beforehand, but these are patterns that are being learned by the model as it tries to get an efficient representation of all the words. And this continuous representation then also allows it to make better generalizations. So if you have seen the word, I will see you on Monday, again, and then you see some input, I will see you on Tuesday again, you can say that these contexts will actually be similar. So you use these continuous representations both on the level of words or even of the whole sentence. And I just want to give you some impression of what this change from statistical methods to neural methods has really done in the last few years. So these are some results from the workshop of machine translation. So this every year there's a shared task, a kind of competition where people submit their systems, and I'm focusing here mostly on systems from Edinburgh, but so this will not be fully representative, but it's not too bad because the Edinburgh system were at or near the top most of the year, so it gives you some impression of where the state of the art was. And you can see some improvements from 2013 to 15, with especially here with syntax-based approaches, and they're actually the winners in those years. And in 2015, something interesting happened. Neural MT came along. It didn't do actually that well in terms of Bleu that year. In terms of the human evaluation, it did a bit better. It was, I think, at that time tied for first place, and that's when we started working on that. And you can quickly see what happened in the next few years. We had quick improvements in the translation quality with neural machine translation. In 2016, it really dominated all the shared tasks, so that we actually stopped working with the statistical machine translations after that. And you can see only focusing on neural, there were still large advances being made. 2018 here, this is a system that's Facebook submitted. So what you see here is like in terms of this automatic risk score, that's like a 50% relative improvement in 3 years, whereas in the previous years it was relatively stable, the quality. So what happened in these years? And again, I mostly talk about the Edinburgh systems here, so it's not fully representative. But the good thing about this shared task is that research ideas from different directions will flow into these systems. So one of the things we did that had a big impact on catching up and overtaking the statistical systems. Um, I said they had this combination of weak models, but one of the advantages that they had is like they had an easy way to integrate monolingual English data. But when you have this end-to-end learn function, it wasn't as clear how you could integrate this. And I'm just showing here the illustration of how this looks. Actually, the decoder side where you're producing your target sentence, and this looks the same for both bilingual data or for a monolingual language model. The difference is here where your source context comes in, where when you have monolingual data, you don't know what comes there. And what we tried to do is to find some approximation or some kind of indicator to say, oh, we don't know what the source is, just do your best. What we found was the best approximation we can get cheaply is by just automatically translating the sentence into the source language. Yes, this will be noisy and it will just be an approximation, but it's actually very effective at allowing us to incorporate monolingual data. Maziar in the beginning has talked about byte pair encoding, so that was another big challenge. When I looked at the translations of the 2015 system, I found that the quality was quite okay for like frequent words, but was doing a poor job at rare words. You have this limitation in vocabulary size with neural methods, and you need to find a way of being open vocabulary. I will talk a bit more about this in a bit. And then every year there is some tweaks to the neural architectures that will have also led to performance improvements. The next year, basically, we learned a lot. We scaled up the models, made them larger, deeper. There's things you might have heard about before, like layer normalization, residual connections, quite standard techniques nowadays in neural networks that were introduced into these models. New optimization strategies like adaptive learning rates. We did more sampling. There was a bit more training data, but that was actually not that much more, not that crucial in getting these quality improvements. After that, in 2018, like the transformer architecture, which replaces recurrent neural architectures, was introduced. It especially allowed um, deeper models, training them faster. So that was a big driver of performance improvements. Also, this semi-supervised training with back translation was scaled up and refined, and there were some other tweaks to training. And just to go back, so with these improvements, we actually have made a lot of progress in the field over the years. So I just want to talk a few minutes about open vocabulary translation, because will be taken up again later when we talk about multilingual models. So we need to have some way of encoding our vocabulary to get the vector representations, and these need to be relatively small and closed for us to be able to train this efficiently. And if you use a vocabulary size of like 10 or 50,000 symbols, you can actually represent like 95% of a running text. And if you only care about automatic metrics, that might be enough. But what you actually find is that the rare words are often those that carry a lot of information. And then if you just leave these out and just transit them as an ANK token, you might get like 95%, or in this example, like 80% of the words, but you're not getting 80% of the meaning across. So the indoor temperature is very pleasant if you just leave out indoor temperature, which is in German translated as a quite rare compound. You're going to have a bad time. There were some previous attempts of just using some kind of backoff mechanism. This wasn't very robust because it depended on alignment. It assumed like having a one-to-one correspondence, which we don't have here. And what we found actually that splitting these words, rare words up um, into subword units was doing a good job at allowing the model to learn the translation. So what we wanted to do is, and this was work done with Barry Meadow and Alexandra Birch, what we wanted to do was having a representation that while it was using a closed vocabulary, was able to represent an open vocabulary as we have in language. And it's not enough to just cover all the words in your training data, because you can always create new words, new compounds in many languages, new names, etc. Um, these two things are actually not that difficult. You could just have a character level representation. But we also wanted to actually minimize the length of the sequence to make this trainable in a reasonable amount of time. So we actually found that we can repurpose a compression algorithm, byte pair encoding from the 90s, for the purpose of word segmentation. Now, originally this was a compression algorithm where you just take frequent pairs of bytes and represent this as a new byte that was unused before. And what we did is we applied this to word segmentation by just taking frequent, starting with a character level representation. We take frequent pairs of characters and just represent this as a new symbol, which is just going to be the word sequence. And you can keep doing this iteratively and just keep merging until you reach the vocabulary size you want. So what is nice about this is that depending on how large you pick your vocabulary, you will have different compression rates. You can see some trade-offs at the bottom. And then you can save the merge operations that you have applied for your training data, and you can apply the same merge operations as well on new unseen data, and you will get a representation where everything will be in vocabulary, unless you have some new characters. Then you have some problems, and we'll get to that later. So I said we've made some big increases in quality in the last few years, and there have actually been a number of widely publicized reports about the quality of translation, like saying Google saying they've now are bridging the gap between human and machine translation, Microsoft saying they've now actually matched human performance, reached parity with human performance, SDL saying they now have near perfect Russian translation. Well, these are big claims. I would say that with strong evaluation protocols, you actually still see some gaps. A student of mine has also looked at this with Microsoft, showing that if you take more context into account in the evaluation, you will still see some deficiencies of the neural machine translation systems. But even the fact that we have to have this discussion is actually a testament to how good these systems have become, because like 10 years ago, they would have been laughed out of the room. And now you have to seriously show, no, we haven't outperformed humans yet in these cases. So is the problem solved? Can we now lie back? Well, I would say no, because while the performance is impressive for high resource language pairs, this is just a tiny fraction of the translation need. You can just see here an illustration of different languages, and these are just like the top 24 languages. And you can see that like almost half the human population actually speaks a language that is not in these top 24. There's actually an estimate that there's like 6,000 languages in the world, and you might be able to get like good systems translating into and out of English between like one of these top 10 or 20 languages. But if you go to the lower resource languages, or if you wanted to translate between two languages that are not English, you will have a much harder time finding these large amounts of training data, like I said, tens of millions of sentence pairs that you need to get really high performance. So this is what I will talk about a bit more today, um, about how can you actually exploit multilingual data. And here I mean multilingual in more than two languages for that. And I'll start talking a bit about transfer learning first. And you might already be familiar with this because transfer learning has really taken off and is dominating all of natural language processing and also other fields. Because with neural methods, it has actually become much easier than previously because often these neural architectures that you design to solve these tasks, these can be shared between different tasks, certainly between different translation tasks. So what is really different is that you feed in different data to your model. You have a different random initialization, but then you have the same training algorithm with the same architecture that you train. Now, what you can do instead of training these separately is to just take a model that you train on task A. Let's say this is one translation directions, and you use this as the initial model for your task B for a different translation direction. And as early as 2016, when neural machine translation was still young, as Alfred have shown that this was quite an effective transfer strategy. I just want to talk a bit more about some research from our groups. This is a student that was co-supervising Aji and joint work with Nick Bogoychev and Kenneth Hayfield. We were looking at what is actually being transferred between these different tasks. Um, Depending on the language pairs that you use, there's some reasonable assumptions what can be transferred there. Like if you have very similar languages, maybe it learns something about this language, learns to produce fluent English output, for example. But interestingly, we also find some transfer improvements if the languages are completely unrelated. For example, here just learning to copy Chinese data from the source to the target side. And it's not as good as having a real machine translation model as the parent, like German English, where you get like a large improvement for these child languages here, Myanmar, Indonesian, Turkish. But where it gets really strange is when you can just train a model to copy random sequences. Like these are just random sequences of numbers, and all it learns is to copy them over. So it learns nothing about language, but you actually still end up with a better initialization, and if you then train these child models, um, you get some improvement. So the hypothesis that was partially confirmed, I mean, the improvement is not as good as just doing real MT model, is that actually what we can learn with this, like just having some random copying behavior that is actually good initialization. It's a good bias to have for neural machine translation models. We were also looking a bit more at this problem of the embeddings, like the language representations. How do you transfer them from one language to another? And there's different strategies that you can follow here. And some of them don't actually make that much sense. Like if you just randomly map the embeddings from your child system to your from your parent system to your child system. There's no meaningful correspondence between what the same embedding represents in the parent and the child. But you still end up actually getting some benefits from doing this random assignment. You can see here, I mean, just transform everything except the embedding already helps, and this is probably partially because of this copying, but there might be other effects here. But then doing also transferring the embedding with some random mapping for some curious reason also helps. I think this is just showing that the random initializations that we do aren't really that good initializations, and there are probably some properties there with this random assignment of these embeddings that are better. But what is actually reasonable that you want to do is that you actually want to transfer as much knowledge as possible. And if you actually have some symbols that represent the same string, it can be a verb or it can just be a subunit or a character. Um, there's some benefit in that. It depends a bit on the language pair that you work with, but even if alphabets are different, you can have like numbers could be the same, or you could have some English inclusions in your other language. So matching these then helps a bit. What you actually can do and what works even better, and what is also quite popular nowadays in multilingual systems, is if you learn your subword segmentation with an algorithm like BPE, you can actually learn this on the concatenation of all the training corpora that you have, all the languages that you have. So learn some representation that is then open vocabulary. You can represent all of both your parent and your child vocabulary within the same vocabulary subword units. So this works quite well and it works the best here. It is, however, not very flexible because you actually need to know what your child languages will be before you train your parent. And this can have some disadvantages, and I just want to give a motivating example here. So in 2010, there was a big earthquake in Haiti, um, and there was a very fast and also well publicized effort by Microsoft to create a translation engine on very short notice to help the people on the ground who came to help after the earthquake. And they actually managed to get from this idea of building a machine translation system to deploying it within 5 days. And this isn't just a training time, this includes data collection, quality assurance, and the actual deployment. So this you really need to be fast for something like this. So if you want to do this for neural machine translation, like having this joint vocabulary leads to this canvas of workflow where you first need to define your vocabulary and then first retrain the parent model. It's not very elegant. You could do token matching here, which is faster and that's okay. But actually last year, or maybe a year and a half ago by now, Kenya may had to propose this alternative where you say, and let us always reuse the parent vocabulary, and we'll just have this universal parent that you can use everywhere. And the problem there is if you have a child language that uses a new vocabulary that you haven't seen in your parent model, um, then one thing you can do is to just Romanize or transliterate it into Latin alphabet. So you're able to represent this with um, your parent vocabulary. And this is an interesting idea, and it's something that a student of mine wanted to look at more closely. So this is work by Chantal Amrine, published at Findings of EMLP. One of the things we wanted to look at, I mean, this is all well to do romanization of some child language when you translate from that language into English. But if you actually want to translate into that language in another alphabet, does a romanization still work? How well can you actually recover the original script, recover the original spelling? This turns out to not be too difficult because a sequence-to-sequence model, like on the character level, can train this quite easily, not too much data, not too long training. The other question that is a bit more complicated is whether we actually can benefit from some knowledge transfer if you use this romanization strategy, and if this is then better than token matching. So we tried this with some parent models of different languages, different scripts, where we used more resources, and then we had some very low resource child languages. And just want to highlight two points that we found and that were quite problematic with this romanization idea. One is that you actually often lose information. This is just here shown with the example of Chinese, where you can see there's different characters that will be represented here in pinyin with the same sequence of characters, like there's ta and ta, and if you don't keep the diacritics, they will look the same. If you keep diacritics, you can at least still distinguish them. But there's also other distinctions that get lost even if you keep the diacritics, because like Chinese words for she and he, the Chinese characters are different, but the pronunciation is the same, ta. So this information loss is something that we found to be quite troublesome. The other problem was that, yes, if you use this subword vocabulary of your parent, you will be able to represent your child language if you have it in Latin alphabet as well. But that doesn't mean that your segmentation is going to be very compact, very optimal from the point of view of compression. So you can see here an example with Amharic, where if you just learn BP on Amharic, you can actually segment this using few long subword units. But if you then reuse the parent vocabulary that was trained on other languages, a lot of these character sequences will not have occurred in your parent languages. So you end up doing a lot more aggressive segmentation, and you can see some subword units here like any, uh, which yes, in English this is quite frequent, but it might not be a good useful unit here. So you end up with much longer sequences. So in terms of results, what did we find here? Well, we found that the good news first, transfer learning actually was useful for, in general, was very useful um, across different language uh, combinations that we looked at, like looking at languages that a new script unrelated to the source or related to one of the parent languages, sorry, unrelated or related to the parent languages. Um, so we always found some improvements there, and token matching worked quite well. If you looked at the romanization, results were a bit more mixed. Um, do see evidence for information loss here, and actually the uconf, which loses less information, was better across the board. When we then compare like where languages are not related, we saw no benefit of using this romanization strategy. At least, I mean, the loss that we saw was relatively small, so it's not didn't work too badly. But on the positive note, we did see evidence for positive transfer, better transfer than with token matching for languages that are related but use different alphabets. Like if you have Hebrew, and this is an Arabic pair, is closely related to Arabic but uses different scripts. Yiddish is related to German but uses different scripts. So we saw a larger transfer performance when you used this romanization, both for the parents and the children. It also works the other direction, like if you have Maltese or Serbo-Croatian, both have used the Latin script, but they have some related languages in the parent language, which don't. So what we found even there, we found some improvements in terms of transfer. So this is something worth keeping in mind if you have some um, if you want to exploit and transfer between um, close related languages written in different scripts, romanization can be an answer. I would say it's still an open question, and I think there's still potential. I think you can do a lot better than this token matching strategy, even for unrelated languages. Uh, if you manage in some way to actually map words with similar or subwords with similar meanings into the same representation and reuse this initialization. This should also help you further down the road. This was now about transfer learning. Now let's look at the idea of training multilingual models, like training one model that can handle many languages, and especially looking at this on a massive scale. Now this is motivated by an application like Google Translate. So at the time, I think it support around 100 languages. Now, if you actually want to support all the possible translation directions there, how many systems do you have to build? Well, it's actually all combinations between them, so that's about 10,000 different translation directions. Now, how do you do machine translation for them all? I mean, there's some possible answers, but they are not very satisfactory. Like you could train a dedicated system for each direction. But that means you're building lots of systems, maintaining lots of systems. This is a huge effort, and it doesn't scale very well because, I mean, I said here, this is 100 languages, but ideally we would go beyond the 100 and try to cover more languages than that. This combinatorial explosion will just kill you. One thing you can do, which I think Google Translate has been doing for some languages or is still doing, is that you just pivot via another language where you have more resources, like you can always go via English. Um, this is not a very nice solution in my mind, because with every translation step you lose some information because there will be translation errors. And also English is not like a useful interlingua, because there's some things, um, some nuances in meaning that can be lost in English, like differences in formality, difference between you and thou was lost, but still retained in other languages. So actually translating from French to German directly, you have more guarantee that you can keep this distinction. So there was this crazy idea that you can just train one model, sharing all the parameters to support them all. And I wouldn't have thought that this would actually work, because of, like, maybe you don't have enough parameters to solve many different tasks. But actually, if your model is large enough, this turns out to work quite well. And it's very simple. You don't even need to change your architecture. All you need to do is to have a special token or some other way of indicating what is the target language that you want to produce for this example. You can have this as an extra input token. And one interesting property that you get as a side effect for free is that you actually can then, with this multilingual model, you can even translate into directions that you haven't been training on. Like here's the example. Assume that you have a model that is trained from English to French, English to German, German and French to English. If you train this model, you can actually use it to translate from German to French directly without going via English. And the way that this can work is that you're exploiting the property of the model that during training it learns representational similarity between words or sequences that have similar meanings, because this is just a relatively compact representation for the model. So if the representation of the English and the German sentence with the same meaning is the same, you're then also going to be able to translate a German sentence directly into French, because it has learned to do this translation. So the closer these two representations are, the better the transfer will work in principle. So today I want to talk a bit about how well this works in practice in massively multilingual models, and what biases there are. And there was some previous work by colleagues from Google who've been looking at scaling this up. Like the first couple of papers, they were just showing that this zero-shot translation works in principle when you have like three handful of languages. Um, but to be really useful, we want this to scale up to like 100 languages, and this is what Aharoni et al. Have tried, like with English to X parallel for like 102 languages. Now, the first results are not actually that encouraging. This is now for supervised direction where you have to use training data. Actually, the average performance tends to go down as you bring in more languages. So that it does seem to be a capacity bottleneck, having more and more tasks that you need to solve with the same number of parameters. That does get problematic. When we're then looking at zero-shot performance, it's also not a great picture, because we see the quality tends to be quite poor, like for Arabic, French. This is abysmal. This is from a scale from 1 to 100. And like if you have a blue score of somewhere between 1 and 5, this is going to be unrecognizable. It's probably some word salad or not even the right language that is being produced. And you can also see that this is quite unpredictable. It goes up and down the quality, even within the same training run. You see these huge differences, like from 15 down to 5 blue. So that can be a problem when you want to have reliable zero-shot quality. So a student of mine, Biao Zhang, and joint work with Phil Williams and Ivan Titov, we were looking um, at this problem in a bit more detail. We actually first created a data set, or extracted this from the opus data collection, because previous work was used closed data. And what we did was here looking at the effects of capacity on the performance of massively multilingual models, and looking at this semi-supervised training, back translation, which I talked about a bit before as being something very useful in getting translation quality up, whether this can also scale to like 10,000 translation directions, or if capacity just is not enough, no matter how much training data you use there. Just a few words on this data set. So this is English-centric, English to 99 other languages. We didn't use all the data we could get our hands on, just like 1,000,000 sentence pairs per language pair. If we could get it for some language pairs, less data was available. So this was about 55 million sentence pairs in total. And this is a respectable amount of data, and these models will take you a few weeks to train. So um, and there's also practical reasons why you don't want to use all the data you can get your hands on. Now, a few words on how we actually increase the capacity of the model. One way to do that was actually just making the transformer deeper, adding more layers. We did find that just doing this naively actually broke training. So in some earlier work, Biao proposed to change the initialization of the model to get properties where the back propagation of the error was more successful and training more stable. So with this, we can train deeper models, and we also looked at language-specific parameters. So the layer normalization is all over the transformer architecture, and it has like bias parameters and scaling parameters, which we made language-specific here. And we can also just add a linear transformation and linear mapping that is specific to the target language on top of the encoder, so after the input sentence has been encoded. Uh, I'm gonna show you some results now, just a few words on how these have been computed. So we wanted to look at different things. We wanted to have a comparison to bilingual models, but we couldn't really train 100 or 200 bilingual models. So we just picked 4 languages, German, Chinese, Breton, and Telugu, for comparing to the bilingual baseline. But then with the multilingual model, actually, we were able to transit in all translation directions. Um, and we can just report averages. And we also picked some translation directions like Arabic to Chinese, Dutch, French, German, Russian, like all pairs between them, where we didn't use any pair data because the training data was just with English, but we can directly translate and evaluate quality. So here's now some results, and I'm going to walk you through them to get some points across. So here, first we look at translating out of English into like 100 different languages. One of the things we find is, and this is nice, this is something we hoped for, that actually making the models deeper helps here. This is not entirely unsurprising. I would say the improvements are larger than those you will see in the bilingual setting. So there is some evidence that capacity is actually more of a problem in this multilingual setting. And even the language-specific parameters, they help a lot here. So remember, these are specific to the target language. So what you end up here is actually for every of these target languages, we have a new linear mapping. But there's also some bad news because the bilingual models, at least on these 4 languages where we tested this on, it still wasn't able to match the quality of the multilingual model wasn't able to catch the quality of the bilingual model. And we could also, of course, make the bilingual model more deeper and better, and then the difference would be even larger. Now, the situation changes a bit if you go in the other direction, if you're translating into English. Deeper models still help, so that is good. But the real good news is here now that we are easily outperforming the bilingual baseline, even our baseline outperforms it, and then the deeper model outperforms it by far. And here you can again see the power of knowledge transfer, because here in all the translation directions you're producing English. So the model actually now benefits from other translation directions, learns to produce good grammatical and English text. And so there's a lot of sharing of information going on here between these translation directions. The target specific parameters here don't help much, but that's actually not a surprise in this direction because the target language is always English. So actually, there's not a lot of capacity we add in this direction. There's only the capacity added in the sense that for the other directions, there will also be specialized, like for English to X, there will also be specialized parameters, which maybe takes the pressure off um, representing um, properties for the other directions also in the foreign language encodings. So let's move to zero-shot translation. Let's look what's happening there. Now, first results are actually quite negative. Um, Increasing the capacity of the model via deep models or language-specific parameters doesn't actually help much, and we are far, far behind even this simple pivoting baseline. So the zero-shot system here wouldn't be competitive at all. Now, as I said before, we wanted to look at synthetic training data, looking at semi-supervised learning with back translation, and looking, can this really scale to like 10,000 translation directions? Now, just because we didn't know how much we would need to produce there, it would be wasteful to translate all your training data into 10,000 translation directions. So we try to do this online during training. So every time we get a training batch, we just for each sentence that we have, we pick a random source language that we want to train from, and then we translate it automatically using the same system into that language, and then we get a new training example. The source sentence might be a bit noisy, but that's okay. It might still be good enough for us to learn something useful. And if you look at the results, you actually find that yes, this is true. It does scale well into these 10,000 directions. And as you see here, even with the baseline, we get like 6 blur improvements on the zero-shot directions with this back translation. And what we also see, which is a nice result, is that now the value of increasing the capacity also becomes apparent. Because we now, from the base to the deeper model, we see an improvement of 4 blur points in the zero-shot translation quality. So we see some evidence here that capacity is a bottleneck if you want to now go from like 100 or 200 to 10,000 directions. But it's actually, I'm surprised that it actually scaled so well to these 10,000 directions. There's a bit of bad news here as well. We did find a bit of quality decrease when we go from English to other languages, which is not surprising because we're basically adding a lot more unrelated tasks um, to the system. So there will be some competition for the parameters between these tasks. And we also not clearly beating the pivoting. I mean, the results here might look good, but if you actually use a deep multilingual model and pivot with that, you can still perform better in automatic metrics than the zero-shot translation. And I looked at some of the translations there, and I would also agree that the pivoting was still doing a bit better. And one of the problems with the zero-shot translation was just the biases that it learned. It actually had learned some tendency to copy like rare words just from one from the source to the target rather than doing some proper translation, which with pivoting this problem we don't see as much. And this copying, this can actually get really, really bad. It can actually happen that like if you're going from if you want to go from French to German with this model in the zero-shot condition, it just produces French again. It just copies the source sentence. Or what can also happen is that it just gets the language wrong. So you want to go from French to German, but what it actually produces is English. So as the last bit in the talk, I just want to talk about how this can actually happen. And the problem here is that some design decisions in the model can cause various biases. For example, if you have copies in your training data, then the model can learn to do that as well at test time. And we've seen that copying can be a useful initialization, and it can be a useful backup strategy um, for the model to do. Like if you have some name that you've never seen before, just copying it into target might be a useful thing to do. But of course, it can also go wrong, like we've just seen here before. Another problem was that if you all our data was English centric, so if the French input is only seen with English output, the model might just learn this association and can just learn to ignore other indicators like the language token, where we tell it what language we want to produce. So in some other work, parallel work to this by Annette Rios and Matthias Müller, we looked at these problems and we looked at how can we reduce the amount of copying, for example, by just changing the subword segmentation, saying instead of sharing it between the source and the target, we learn this independently, and you can see here for like names, what you can now end up with having different segmentation. Oh, actually, the example here, uh, no, here, Donald, um, you can see different segmentation, so you won't just be able to learn to copy this over. And this helps reduce this copying bias of the model. Or this bias that it just learns to produce English if the input is French and ignores this language token. You can reduce this if you make sure that every input language has been seen with at least 2 different output languages, even if it's just small amounts. And that is enough to force the model to pay more attention to this. And in the interest of time, I'll just go through this very quickly. You can see for the supervised language pairs where you have trained data, you actually don't see improvements. And this is maybe why zero-shot translation still had some trouble actually um, being improved a lot over the years, because we're not optimizing for that. We're not basing our design decisions on actually improving the generalization to these zero-shot translations. But if you actually do that, and we do like have this specific language-specific byte pair encoding, we see some improvements when we make sure our training data is not only English-centric. We see other large improvements. So we see like on average 10 improvements here for the zero-shot direction. So this is quite substantial, and also in this work made the difference between being below and slightly above this pivoting baseline. So what are some lessons we have learned from multilingual machine translation? Well, I think one big lesson is that this really works well, no matter what you do, even if the languages are not related. There's a lot of transfer going on there, and for a lot of low resource language pairs where you don't have a lot of data, this is one of the most effective ways of getting translation quality up. The massively multilingual models, I think they're interesting. They have a lot of potential to also simplify the deployment of machine translation many directions. We've seen that capacity is crucial, and that really, if you want to be able to generalize to zero-shot direction, we have to be careful about the design decisions we make there. We've seen the correlations that we learned from English-centric models. We are now moving away from these models. Other groups have also moved away from that a bit. We see that we, if we can get data, we should use that. Parallel data is of course great, but even if you can't get that, creating synthetic data helps. And we've seen in a few ways now how language representations can matter. I talked about romanizing data that can help transfer between related languages in different scripts. Sharing subword segmentation in general can help to transfer between languages in multilingual settings. But we also saw that it can exacerbate this copy behavior, which can be undesirable in some context, like in the zero-shot setting. Okay, that's it from me. Thanks for your attention. Here's some link to some code, and I'm happy to take some questions now.